I have alluded many times over the past several lectures the principles that I'm going to focus on today. So thankfully what I'm saying are there many of the ideas you've seen before. I'm just putting them together. It's the idea, the primary idea, is that I've talked about rotation and translation as linearly independent motions, that an object can be observed in the context of its translation. Look at its center of mass. Its center of mass has a velocity moving this way, and all parts of the mass moving this way, say along the x-axis, whatever. And then independently of that, I can look at an object as having an axis of rotation, and it rotates about that axis. That's another kind of motion that it has, independent motions. But there are many circumstances that I know where I observe an object that translates and rotates simultaneously. Now, if I take an object like the hammer that I used in a previous lecture and I throw that through the air, it moves with its center of mass moving as a projectile as it flips end over end. That would be an example of translation and rotation simultaneously. But in that case, the translation and the rotation are ultimately independent. The one has nothing to do with the other. The dynamics of those things can be treated absolutely separately. But there's a special case of rolling and of rotating and translating that we want to look at, and that is rolling. In fact, the title of this lecture is rolling. I want you to consider what I've just said. I'm going to draw some diagrams about to sort of illuminate what I just said in words. I have an object here, perhaps it's a disk. This is a challenging diagram to draw because I'm going to have to draw 3 disks that look exactly the same size, same sort of location. This will be a bit of a challenge. And imagine that this disk is translating only translational motion. So I could look at the center of mass of the disk here, which is like right in the center, and say that it has a velocity which is VCM, the center of mass velocity of the disk, and there it goes. But if the motion is purely translational, then every point of the object, every bit of mass of the object has that same velocity, VCM. That is, if I look at a point down here at the bottom of the disk, it also is VCM, and I make sure to draw that vector of the same length. And up here, I'll draw a vector VCM which points this way, VCM like that. And everything is moving with the velocity of the center of mass like that. But now consider purely rotational motion. So I have to draw the same disk again. I've done a fair job of it, not a fantastic job. I'll actually give it one more try because I'll give it another try after that one. 3rd time's the charm or something like that. Okay, that's good enough. Right? I think I'm close to having those. That's as good as it's going to get, really. And imagine this is purely rotational motion. If I'm looking at purely rotational motion, then the center of mass position does not move. It's the axis of rotation in this case. And if I look at the top of the thing, let's say the top of the thing is moving this way with a velocity v, and moving this way, the bottom part here, if I look at the bottom, is moving this way. You see, because it's rotating, there'd be a tangential velocity, and I could draw velocity vectors all the way around as a point on the edge of the wheel goes around and around in purely rotational motion. Well, now what I want to do is describe a situation where an object is rolling. And I suppose I should have got the disk out so I could, roll something, but it's not very, I'm going to do that anyway. But it's not very illuminating, just like watching a thing roll. Perhaps I'll get some use out of this demonstration apparatus. Here we go. This is a disk that we're familiar with. It's the same wooden disk that I used before. But now I place it here and I observe it's rolling, which is certainly translation. I can watch the center of mass of the thing and it moves along the table. And I know that it's rotating because there's an angular displacement as it turns over and over. What I'm interested in primarily is the point of contact of the disk and well, it's very courteous here, moving along nice and slowly as I talk about it. The point of contact between the disk and the table as it rolls. There is no slipping going on here, right? If I were to grab the disk in my hand and push it, I can slide it across and there's kinetic friction between the disk and the table. But as I watch it roll, the angular, I was going to say angular displacement. What I mean is the arc displacement of the disk is equal to the translational displacement of the disk along the table. So as it rolls down, it's rolling, every time it rolls a meter of arc length, it rolls a meter along the table. This is rolling without slipping. Rolling without slipping because there's no relative motion between the point of contact of the bottom of the disc and the table. It's kind of a difficult thing to get your head around because the disc is moving. But the surface of the outer edge of the disc is not moving relative to the table. That is, the relative velocity is zero. Since the relative velocity is zero, that means that the tangential velocity of the disc must be the center of mass velocity, and I can put that notation there. In the case of rolling without slipping, there's another kind of rolling, which is called skidding, and I'm going to address that. But for the moment, rolling without slipping. So the tangential velocity must be equal to the translational velocity in order to roll without slipping, so that the relative velocity between the point of contact of the bottom of the disc and the surface of the table is zero. How do I describe the total motion of rotation and translation simultaneously? The answer is kind of cute and clever, is vector addition. I'm going to drop a plus sign between these two diagrams because I'm going to add the diagrams together. And my addition will be vector addition. It'll be vector addition. I'll add velocities, but I'll add them according to their directions as well. Now here I have to write, well, I'll write an equal sign first. I'll write an equal sign, and now I have to draw my third absolutely the same disk. Not good enough. I gave myself 3 chances the last time. I'll give myself 3 chances here. I only need 2. No, it's not big enough. Third time. Third time. Here we go. That'll have to do. Look down at your notes and see if your diagram looks better than mine. Adding vectors here at the point on the top of the disk. According to the translation, the top of the disk is moving with a velocity VCM. According to rotation, the top of the disk is moving with a velocity VCM. And so the top of the disk is moving with a velocity 2 VCM. I've just added those vectors together. That's the velocity that the top of the disk is moving with. Looking at the center of mass of the disk, which is also the axis of rotation in this case, or how I'm thinking about it at the moment. In the translational diagram, it's moving with a velocity center of mass, but the center of mass in the rotation diagram is not moving. So I add those two velocities together, and what I get is VCM, the velocity of the center of mass. Looking at the bottom point, the point of contact, where the disk rests on the surface, I have the velocity of the center of mass directed to the right in the translational diagram and to the left in the rotational diagram. They are equal in magnitude, opposite in direction. The velocity there is 0. And so I've achieved in this diagram what I observed by rolling the disk, that there is no relative motion between the point of contact of the disk and the surface. Now, you might imagine that there's some frictional interaction there. If there's a frictional interaction there and there's no relative motion, the nature of that frictional interaction must be static friction. Must be static friction because kinetic friction is associated with the relative motion of surfaces. That's just a little aside. We'll come back to that because I'm going to solve problems with friction in, and you'll see. Blake.
Is there nothing that goes downward?
Rolling across the table, see, Blake, I know what you're thinking, and it's a very, very difficult, challenging thing. Because what you're imagining now, Blake, I think, and maybe what I'm about to do is to help you imagine it, is that in the very next instant of time, this disk is going to rotate into the surface. Because now you've started to look at this as the axis of rotation, with this velocity of center of mass being a tangential velocity, and naturally the velocity of the thing twice as far away being a tangential velocity twice as large. And so you, I think, I'm going to put words in your mouth, but I think I've started to think of that as an axis of rotation. And if that's so, you know what, you should probably just right now announce that, yes, that is what you're thinking, because if that's what you're thinking, you are dead right. Absolutely right. I'm going to change my thinking for rolling without slipping so that the axis of rotation is not the center of mass axis that I started with my discussion, but instead the point of contact with the surface of the table. And that's troubling. Because what's going to happen in the next second is that the disk, if this is its rotation, is going to rotate into the surface. That's not true. The surface is the solid, and the thing's solid. It doesn't rotate in. The axis of rotation is moving along. It is, in principle, rotating about an axis of rotation that is moving. It's kind of like orbital mechanics. You're falling towards the Earth, but the Earth is curving away. Yeah, you see? Very, very difficult to get in your head. Luckily, the math works itself out quite easily without having to do any kind of that machination. Point is, it is fair play when I'm doing rolling without slipping to take the axis of rotation to be the point of contact between the object and the surface upon which it rolls. And I'm going to make very, very great, I'm going to take advantage of that in a very, very significant way in just a moment. All right? Here's a point that I want to make here. It's one that I've already made, and I said later on I'll assert that. The only way you can roll without slipping is if the translational center of mass velocity is also the tangential velocity, and vice versa. The tangential velocity is equal to the center of mass velocity. That is the only way you roll without slipping. That makes it a requirement of this arrangement that omega be equal to V over R. Now, in some previous derivations, I've made that assertion. We've done some conservation of energy, where the rotational kinetic energy appears 1/2 I omega squared, and I've substituted for omega V squared, or pardon me, V over R. Substituted for omega squared, V squared over R squared. I made that assertion, but that assertion is assuming that the tangential velocity and the translational velocity are the same. That is, I was making the assumption of rolling without slipping before I had actually explained the nature of rolling without slipping. If an object is skidding, then the center of mass velocity here and the tangential velocity here, they're not the same. And so this assertion is invalid. So this equation, and also the angular equation and the angular acceleration equation that are associated with it, that is, theta is equal to S over R and alpha is equal to A over R. Those three assertions of the relationship between the angular and the translational quantities is only true in the case of rolling without slipping. So what I'm going to do now is solve a problem of rolling without slipping, but in true physics fashion. I'm going to solve it two different ways to show you an advantage of this kind of thinking about rolling and how it applies. So here I go, rolling without slipping. And in the spirit of yesterday's conversation, not during a lecture, but off the lecture, we talked about the moment of inertia of a sphere. And in a study session, we derived the moment of inertia of a sphere, which is 2/5 mr squared. And finding that moment of inertia is sort of a feat of calculus. What I'm going to do now is roll a sphere down a ramp, which is a thing that I do in introductory physics. Roll a sphere down a ramp and then talk about its velocity at the bottom of the ramp. But of course, you know that we did not account for rotation when we did that. So in introductory physics, when you first roll a ball down a ramp, your answer is wrong because it does not account for the rotational motion of a ball as it rolls, which again, I've said before, is the reason why we slid boxes down ramps, because the box doesn't rotate, and so that you get an answer that is more true, and you're not sort of cheating the student. Using my board effectively as possible, strangely enough, I'm going to start here and then move off into the great space over there. I don't have any choice. What I need is an incline and a sphere of mass m that I can roll down this incline. It's inclined at an angle theta. So here's my incline, and here is my sphere that I'm going to roll down. I drew a giant sphere, I know, because I need to talk about the forces that act on the sphere. So I normally wouldn't draw something so comical. I want to find, my goal in this solution is to find the acceleration of the sphere down the incline. Warning, I don't know the coefficient of friction. I don't know the coefficient of friction. I want to find the acceleration of the sphere down the incline, but the coefficient of friction can't be in it, not allowed. there are some forces that influence the motion of the sphere. There is a weight force which acts at the center of mass of the sphere. And because I'm talking about rotation, where that force acts turns out to be important to my analysis of this. There is a normal force of contact between the sphere and the surface. Now, boy, doesn't that look strange. I've drawn it from its point of action straight through the center of mass and off into the air perpendicular to the incline. It's a little troubling. Now, there is a friction force. The nature of the friction force is static because I'm talking about rolling without slipping. That means there's no relative motion between the surfaces. The nature of that friction force will be static. But what direction shall I point it? Well, it has to point in a direction that will cause, yeah, I'm getting signals from the audience that it should point up the incline. It has to be pointed in a direction that will cause the angular acceleration that I expect. That is, the force of friction must cause a torque that will rotate it, in this diagram, in a clockwise fashion so that it'll roll. As a matter of fact, the friction is the cause of the roll. I might try to trick you in some exam that you take somewhere where there's no friction. If the incline is frictionless and I release the disc, it will not roll. It will translate down without rolling. It's a strange thing because it never happens in real life, right? There's always friction, and so something always rolls if it can, right? The friction will always induce some kind of rolling. But if you saw it in real life, it'd make you a little bit queasy. You put the disc there and it would just go down without rolling and then go along without rolling. You'd be like, that's not right. Something's not right. Also, imagine that I have a situation where I roll a disc on a frictionless surface and it's rolling and it hits a frictionless incline. As it went up the frictionless incline, it would continue to rotate with constant angular speed because there's no friction to produce a torque to stop the rotation. So it would just continue rotating even though there was no longer friction available. Sort of rotational inertia. So this is my free body diagram drawn on the thing. And what I want to do is find the acceleration. Well, to find the acceleration, I'm going to redraw my free body diagram here, but I'm going to draw it a little bit smaller so I feel a little bit better about how I've drawn things. I'm going to draw the components of my forces, and I'm going to draw my traditional force, mg cosine theta here, breaking the weight force down into its components perpendicular and parallel to the incline because I find that useful in inclined plane situations to do that. The normal force is directed this way. The normal force is directed this way, and the friction force opposes the motion. Friction force is directed this way. And that's a very common looking free body diagram, isn't it? Very common looking. Well, I'll apply Newton's second law to this free body diagram, and I'll write the sum of all the forces is equal to the mass times the acceleration. I don't think anybody will object if I just write it. I don't think it'll bother anyone. The force directed down the incline is mg times the sine of theta. And I'll call that the positive direction down the incline because that's the direction of the motion. mg times the sine of theta minus the friction force, which is mu times the normal force. And looking at my free body diagram, the normal force is clearly equal to mg cosine theta. So in a way that's very familiar to me, I'm going to call this mu mg times the cosine of theta, and that's lovely, is equal to the mass times the acceleration. I wonder, and I don't know if I'm right about this, but I'm actually flashing back to my own experience learning physics for the first time. I wonder if you're looking at this thinking, yeah, but Shadi, you're not accounting for the fact that that is rolling. You're doing Newton's second law and like pretending like the thing's not happening. You can do that. I can draw a free body diagram and apply Newton's second law to it and pretend like rotation doesn't even matter. Isn't that groovy? I can do that. So what will the acceleration be? Well, the acceleration is quite obvious here. The m's cancel, and I don't even have to solve it algebraically. I have my answer. Yay, I found the acceleration pretended like acceleration. You see? At the beginning of the problem, I stated a caveat. I don't know what the coefficient of friction is. I don't know what the coefficient of friction is. I can't have it in my answer. And there it appears. I claim that the acceleration is g sine theta minus mu g cosine theta is equal to a. There's mu. Not allowed to have it. I need to find a way to eliminate it. So to eliminate the coefficient of friction, I'm going to write Newton's second law for rotation. So I'm going to write, and now here, since I'm doing this for the first time, I know things are happening in a squirrely way. I'm going to write the sum of all of the torques that act on the sphere is equal to the moment of inertia of a sphere times its angular acceleration. Well, surely When I apply this rotational Newton's second law, I have to choose an axis of rotation. And I'll choose the center of mass to be the axis of rotation. Why am I choosing that? I'm choosing that because yesterday afternoon, I was in a study session where I derived the center of mass of a sphere about its center of mass, because the center of mass of a sphere is at the center. So I know that it's 2/5 mr squared. So I'm going to do a little 2/5 mr squared here for the moment of inertia on the right-hand side, because I know that's center of mass. Yeah?
You said you derived the center of mass relative to the center of mass.
I'm sorry, I derived the moment of inertia relative to the center of mass. I misspoke.
Just wanted to make sure. That'd be a little odd.
Like this.
Yeah, just like this.
I meant when you put it online.
Yes. Yes. And so I have to choose the axis of rotation, and I choose the center of mass axis of rotation. And the reason why I choose that is because yesterday afternoon in a study session, I derived the moment of inertia of a sphere about its center of mass axis. And so I know it. It's 2/5 mr squared. And so I'll use that on the right-hand side of this equation. So I have the sum of the torques. Well, what I have to do is look, on my diagram here, if the center of mass is the axis of rotation, of all of the forces that act, which exert torques? Let's consider the mass. Does the mass exert a torque? No. Certainly it's a force applied to the sphere, but it acts at the center of mass location. It acts at the axis of rotation. Therefore, it produces no torque. Does the normal force produce a torque? The normal force does not act at the axis of rotation, but it acts through it. It's like me pushing on the door toward the hinges. That does not produce a torque. The only force in my diagram that produces a torque is the force of friction. That is the only force that produces a torque, because the friction acts perpendicular to the radius of the sphere and is at a distance from the axis of rotation of the center of mass. So when I write the net torque is the force of friction. Now the force of friction is mu times the normal force, which is mu, times mg cosine theta. That is the force of friction.
Would you not need to make that negative?
I do not need to make it negative, because at this point in the problem, I can choose which direction I call positive. So I'm going to call clockwise rotations positive. So this is a positive torque, because it would act to rotate the system in the clockwise direction that I arbitrarily choose to be positive. So I'm safe that way. So this is mu mg cosine theta, but that's just the friction force. I need to multiply the friction force by r. And I've put the r in front of the cosine because I always like my trig functions to be last in any expression, so I don't confuse the argument of the trig function. So mu mgr cosine theta is the torque exerted by the friction force must be equal to the moment of inertia, which I now know, is 2/5 mr squared. And now alpha, the angular acceleration. But I'm making an assumption of rolling without slipping. And the condition of that, rolling without slipping, is that I can write alpha as a divided by r. And once again, we get in the habit of doing these things. You see a pleasing thing happens to this equation. That an r appears here, which cancels one of the r's in the numerator, and then this r cancels the r on the other side of the equation. I also have a mass here, which cancels a mass there. And so what I have left over is that mu g times the cosine of theta is equal to 2/5 of a. Well, down here in my equation, mu g cosine theta appears. And here mu g cosine theta is equal to 2/5 of a. So I'm going to quite shamelessly take this thing down here and make a substitution, such that g sine theta minus mu g cosine theta, which I now know is equal to 2/5 of a, is equal to a. So now I found my result here, and I'm just going to just absolutely shamelessly draw arrows all over the place here. I found my acceleration because what I'm going to do is take 5/5 a and add 2/5 a to it, and find that I get 7/5 g sine theta. 7/5 of g sine theta, which is a pleasing result. Yes? This is 5/5, and I'm adding 2/5 to it. That's 7/5. And then I divide it. Thank you. Sorry. My bad. All right. 5/7. Oh, and that's really important, too, based on the next thing I'm going to say. It's a very pleasing result now that we've corrected it. Because if this were a block sliding down the incline with no kinetic friction acting, no kinetic friction here is static friction. The rolling friction is static friction. There's no kinetic friction here. If a block accelerates down an incline with no kinetic friction impeding its motion, its acceleration would be g sine theta. But here, with the rolling involved, because some of the action of the motion is going into rotation, I expect the acceleration to be less. And indeed, it's a fraction of g sine theta because of the rolling. So that is an object rolling down an incline, the dynamics of it. Important feature of it is I shamelessly applied Newton's second law for translational motion with no account for the rotational motion. And then because of my requirement that I wasn't allowed to have the friction coefficient in it, I had to do some extra work involving the rotation. Yeah.
So that means even if there was no friction, the acceleration would still be the same, whether it be a sphere or a block. It would still be just g sine theta.
Yes. Because if there were no friction at all, there would be no rotation. And it would slide down like a block, not rotating, only translating. Blake.
So when it's like you were saying earlier with like moving without friction, it would like roll. Is that like when you hit like an air hockey puck and it just like kind of glides and then you can't see it?
Well, that's motion without friction, but of course a puck is not rolling. It would never rolls.
If you hit it sideways,
Imagine instead that you take a bowling ball to the ice rink.
no, but even when you throw a bowling ball, there's like a certain amount of
Yes. Yeah, we are going to solve that problem. It's actually part of the lecture. We are going to solve that problem. I hope so. But imagine you take a bowling ball to the ice rink and you bowl a bowling ball on the ice rink. It will slide along without rotating. There'll be a little bit of rotation. It'll start to slowly begin to rotate, but by and large, it will slide without rotation, just slowly starting to gain some rotation because there is friction between a bowling ball and the ice, but very little. And so it would just sort of go along translating but not rotating.
With what Brad said, the circle and the sphere and the block sliding down at the same acceleration, wouldn't they have like different amounts of friction? It would be like
He said without friction, so in the absence of friction.
okay.
Yeah, in the absence of friction, that's what we would see.
Okay.
And going along with the theme of the past, several lectures, I'm going to solve the problem again. I'm going to solve it again. I'm going to solve it the smart way. But it's hard to imagine that this is the dumb way of solving the problem. I'm going to solve it again. I'm going to solve it the smart way. So here I go again. And obviously, it being the smart way, I'm going to require less room on my diagram. So here, as a matter of fact, you know what? I'm going to use the same diagram. Why redraw the inclined plane when I'm just going to draw the same thing again? Don't even need a new diagram. I'm just going to put a little wavy line here to say I'm doing a different approach. I'm going to solve the problem again. Remember, my goal is to find the acceleration. Don't blink, because it's going to take me very little time to get it. I'm going to choose as the axis of rotation, not the center of mass. Not the center of mass, but the point of contact. I'm going to choose the point of contact as the axis of rotation, which in the case of rolling without slipping, I've demonstrated I can do instantaneously. Choose the point of contact to be the axis of rotation. No problem. So I'll do that, and I'll start from the sum of all the torques is equal to the moment of inertia times the angular acceleration. And now observing the torques again, I ask the same question as before, but I ask, which forces cause torques? The friction force acts at the axis of rotation now. it produces no torque. The friction force now acts at the axis of rotation, and therefore it produces no torque. The normal force acts at the axis of rotation. It produces no torque. The weight does produce a torque. Here is the weight vector acting at the center of mass position directed downward. The weight does have a component that is perpendicular to the moment arm. That component happens to be mg sine theta. The other component of the weight, mg cosine theta, acts through the axis of rotation and therefore does not produce a torque. So the only torque acting on the system here is the torque caused by the force of gravity, which is mgr sine theta, the component of the weight force that is perpendicular to the moment arm and produces a torque multiplied by the length of the moment arm, which is the radius of the thing. Well, Shiley, wow, you're getting away with murder here. That's easy. Now there's no friction at all. There's no mu in it. Well done. There's a trade-off. What is the moment of inertia? It's not 2/5 mr squared, because 2/5 mr squared is the moment of inertia of a sphere about its center of mass axis. And that is not the axis that I have chosen. What shall I do? That's right, parallel axis theorem. Why not? Because the parallel axis theorem tells me that if I know the center of mass moment of inertia of a regular object, like I do, 2/5 mr squared, all I need do is add to that m times d squared, where d is the distance between the center of mass axis of rotation and the new axis of rotation that I've chosen. Well, that distance, you can see in my diagrams, the distance between the center of mass and the point at which the sphere contacts the surface is r. So all I have to do is add a little r squared to it. That's a fair trade-off. I'll take that. Moment of inertias are always mr squared.
No, the parallel axis theorem.
Parallel axis theorem dictates that it should be so. Multiplied by alpha, which again, because I'm rolling without slipping, I'm going to assert is a over r. Shoot. I'm going to assert is a over r. Like that. Shall I gather terms? We know all the r's are going to go away, right? We're getting experience with that. All the r's are going to vanish. And the m's are going to vanish too. Why not indeed? Just go for it. So g times the sine of theta, oh, that's nice. I feel like I'm being productive here, is 2/5 plus 5/5, oh look, is 7/5 times a. And so 5/7 g sine theta is equal to a. The same result with fantastically less effort. So in the case of rolling without slipping, choosing a coordinate system where you eliminate forces, because I can choose my axis of rotation to eliminate a force by selecting the location that force acts, and then it exerts no torque in that coordinate system. The trade-off is I may have to parallel axis theorem in order to get what I want out of that. So it was just suggested that when you bowl, apparently someone has had the experience, and that's good because I'm about to demonstrate this problem. That when you go bowling, grab hold of a bowling ball, and you approach the lane, and you swing your arm. When you release the bowling ball to the floor of the alley, and I think if you're doing it correctly, you sort of just, you get your body mechanics right, so you just touch the lane and release the ball. The ball is released with zero angular velocity. The ball is not rotating. And as it goes down the lane, it slowly begins to rotate by the torque exerted on it by kinetic friction. I say kinetic friction because it's skidding. The surface of the bowling ball is sliding relative. Up to this point, I've been talking about rolling without slipping. This is rolling with slipping. This is skidding. So this is a very essential problem I'm going to solve. If you'd like to give it a name, skidding to a start would be a good name. You see, we've done skidding to a stop. This is skidding to a start. As a bowling ball, initially non-rotating, begins to rotate. Now, what will happen is the basic idea that we should be thinking about, is that the angular velocity of the bowling ball starts at 0 and increases. And the translational velocity of the bowling ball starts at some initial value and decreases until the translational velocity and the tangential velocity of the bowling ball are equal. Because when the tangential velocity of the bowling ball and the translational velocity of the bowling ball become equal, then the relative velocity between the surface and the surface of the bowling ball is 0. And then I'm rolling without slipping. So what I'm going to do is write down very carefully these conditions and solve. We'll see what happens. So here I have, for a diagram, what do I need? I need a bowling ball. It's all spheres today. So I need a bowling ball. I know its moment of inertia is equal to 2/5 mr squared. I just made use of that in the previous problem. And so I have a bowling ball that has an initial velocity v0, that is its center of mass, and all of the bowling ball is traveling with an initial velocity v0. But its initial angular velocity, omega 0, is equal to 0. So I probably want to investigate what forces are acting on this, and I already put a velocity on that diagram, so it's not really a force diagram. Consider then this diagram. The weight acts at the center of mass of the bowling ball, which is mg directed downward. There's a normal force that acts on the surface like that. That's the normal force directed that way. And there is a friction force that is causing the bowling ball to rotate in a clockwise manner. And that friction force is directed this way. The nature of that friction force is kinetic. The nature of that friction force is kinetic. And let's say that there's a coefficient of kinetic friction here, mu k, between the bowling ball and the surface. I will not be able to eliminate. Actually, let me write mu k is equal to mu, because I don't want to carry that k around all over the place. So I'm just saying wherever mu appears, it is the kinetic friction coefficient. And so how am I going to treat this thing? Well, the first thing that I want to do is apply Newton's second law to it in its translational form. So for the bowling ball, I'll write that the sum of all the forces that act on the bowling ball is equal to the mass times the acceleration of the bowling ball. It is the horizontal motion of the bowling ball that is interesting. If you look at my free body diagram, clearly the normal force directed upward is equal to the weight force directed downward. So I have no need to solve that. So I'm simply going to look at the friction force and how the friction force affects the horizontal motion. Here I will put a negative sign. And I'm putting that negative sign there for the friction because here the friction force is acting in the opposite the direction of motion, which I choose to be positive. So the positive direction is to the right, the friction force is directed to the left, and so I put it negative in my Newton's second law equation. Is mass times acceleration, and then here I get a rather familiar result, or hopefully very, very familiar to me result, which is that mu mg is equal to m times a, and the m's cancel such that negative mu g is equal to the acceleration of the bowling ball. So I've applied Newton's second law to find the translational acceleration of the bowling ball, and therefore I can write with great confidence that the velocity of the bowling ball at any time is equal to the initial velocity plus the acceleration times time, because this acceleration is going to be constant because the normal force is constant, therefore the friction force is constant, therefore the acceleration is constant. Inserting that acceleration, the velocity at any time is going to be the initial velocity minus mu g times t. And that's not surprising. Because of the action of the kinetic friction force, the velocity of the bowling ball will decrease. Notice once again, I have not even considered yet the rotational motion of the bowling ball because the rotational motion and the translational motion are independent one of the other. Now let me consider Newton's second law for rotation. The sum of the torques is equal to the moment of inertia times the angular acceleration. The sum of the torques is equal to the moment of inertia times the angular acceleration. Well, what forces cause torques? Well, if I'm going to do a rolling thing, I'll choose. Maybe I would choose the point of contact with the surface to be there, but then the friction force vanishes, and when I do that, there's zero net torque on the thing. So I'm going to choose the center of mass axis for this calculation because I want the friction to appear in it. Right? I want to get that angular acceleration that's caused by it. So, does the weight produce any torque? No, it acts right through the center of mass. Does the normal force produce any torque? No, right through the center of mass. But the friction force does. So the torque exerted by the friction force, which I'm going to write as positive because I choose the direction that's positive, and I choose, once again, that clockwise torques are positive torques. And the friction force acting alone would rotate the bowling ball in the clockwise direction. So, once again, I'm going to write the force of friction, which is mu g cosine theta, and multiply by the radius of the bowling ball in order to get the force of friction. Because the normal, whoa, watch me being wrong. I'm like in my brain stuck in the old problem, aren't I? Pardon me. It's just mu mg times r. Why did I put a cosine theta in there? That was insane. It's just mu mg times r. Yeah, solving problems and doing stuff. It's just mu mg times r. And so that's equal to the moment of inertia times the angular acceleration. The moment of inertia is 2/5 m r squared. Alpha. You go, oh no, Shidley, alpha, that's a over r. Alpha is a over r. No, it is not. Because I cannot substitute a over r for alpha in a condition where I'm slipping. When I'm skidding along, there is not a connection between the translational motion and the rotational motion. I can't make those assertions. I can't say S is equal to R theta. I can't say V is equal to R omega. I can't say A is equal to R alpha. I can't make those assertions when I'm skidding. So I have to leave it as alpha. But, you know, I've figured out what alpha is, and maybe I like that. I'll cancel an M over here and an M over here. I'll cancel an R with one of the R's over here. And what I get is that 5 halves, what do we have? Mu G over R. 5 halves mu G over R is equal to the angular acceleration. And that angular acceleration is constant because mu is a constant, G is a constant, R is a constant. It's all constants. That angular acceleration is constant, and so I can make a kinematic assertion that omega is equal to omega naught plus alpha t in the case of motion with constant angular acceleration. And now I know what the angular acceleration is. And I know that the initial angular velocity is equal to 0. So please let me just strike that out and call it 0. So the angular velocity at any time t is equal to 5 halves mu g over r multiplied by t. Notice, it's positive. The angular velocity starting at t is equal to 0 will be 0 and will increase. So my equations are predicting the dynamics that I expected. It's just my general description phenomenologically of how the bowling ball behaves as it skids. So now with these two equations, that the velocity is equal to the initial velocity minus mu g times t, and this equation that the angular velocity is equal to 5 halves mu g over r times t, I want to ask the question, how much time passes before it begins to roll without slipping? For how many seconds does it skid before it begins to roll? And I can calculate that by making the assertion that when it rolls without slipping, V is equal to R omega. That assertion is made when it's rolling without slipping. So I'm going to force that to happen. And when I force that to happen, I can write omega here as V divided by R. So omega is equal to V divided by R. So what I'm going to do is I'm going to take V and divide it by R by taking my kinematic equation here, V naught minus mu gt, and dividing every term in it by R. So V naught divided by R minus mu g over R times t. So I've just taken my kinematic equation, divided it by R. That must be equal to omega. And omega is equal to, just have to substitute here, 5 halves mu g divided by R times t. Now t is what I wanted to know. T is what I wanted to know. So algebraically, I just have to solve for it. I'll get t all on one side by adding mu g over r to the side. Luckily, notice this is a mu g over r term, and this is also a mu g over r term, so this is nice. I'm going to add 2 halves mu g over r t to 5 halves. So what I'm going to get, I'll leave over here on this side v naught divided by r, and on this side I'll have 7 halves. Because of 5 halves, I've added 2 halves. 7 halves mu g over r times t. Notice now, then I had it before, but now it's very conspicuous that I have an r on this side and I have an r on this side. And so all I need to do now is solve for t. And that's going to be 2/7 v0 divided by mu g is equal to t, the time it takes for the bowling ball to stop skidding and start rotating. You say, oh, wait a second. I've got a different problem, a different version of the problem, where it says, how far does the bowling ball travel before it starts rolling without slipping? We say, well, that's no problem. If I'm looking for the displacement and not the time, I'll simply start this part of the derivation with v squared is equal to v naught squared plus 2a delta x. And this part of the derivation I'll do omega naught squared is equal to omega naught squared is equal to omega squared is equal to omega naught squared plus 2a delta theta. No. Cannot do that. Cannot make that assertion. And the reason why is that because skidding is taking place, the angular displacement of the bowling ball and the translational displacement of the bowling ball are unrelated. Both motions happen in the same time, but they don't happen in the same space. So if I wanted to know how far it travels, what I would have to do is take this time that I calculate and then go back to a kinematic equation using the acceleration of mu g, and the equation I would use obviously would be x is equal to x naught plus v0t plus 1/2 at squared, and solve for the displacement in that time. Have to be careful not to do it the other way around. And there you have it, a bowling ball skidding to a start.